let's begin another topic that will tie into partial derivatives and functions of two or more variables. As you can see by the title, this is called the directional derivative. And if we were to let z equals 4 minus x squared minus y squared, we could say that that is the same as f of xy equals 4 minus x squared minus y squared. So, can you pause the video? Would you pause the video, please? See if you can sketch this picture before you see me unveil it. Okay, so I'm going to slide my cover off, and you're going to see two pictures, but the one that you're concerned about first is this picture. I'll tell you about the other one shortly. Right, so z equals 4 minus x squared minus y squared, and I didn't put it on there, but the origin is here, and this would be our x-axis and our y-axis. And I didn't include those on purpose because I think trying to imagine them and filling in those blanks is a never bad exercise, especially if 3 dimensions intimidates you a little bit. So 4 units up, and it opens downwards. It's the parabola bowl, I like to nickname it. Now I want you to imagine that you're standing at some point on the surface above the xy plane of this graph. Let's suppose that we were like right here. Suppose we were right there at that point on the paraboloid. Now if we were to do a top view of that circle right there, we would know this circle better as what was called the level curve, and it happens to be when z equals 3 exactly. Now, if this is the positive x-axis and this is the positive y-axis, then that would be the negative y-axis. So I think that point right there is perhaps right about here on the circle. So here's where the concept of directional derivative comes in. You're standing on the side of the mountain. It's probably not going to be this steep if you're actually standing on it, because you might be sliding if it's this steep. So you're standing at this point in the mountain, and so I want you to think of the top view. So as far as you're concerned, it may be uphill and downhill depending on which way you go. But if you're standing upright, and your head is pointed in the z-axis direction, and your feet are at the bottom. So the question is, if we were to, let's say, face this direction and aim that way, what would happen on this graph? So we're standing at this point and we face this direction, we go that way. Well, I think we would find ourselves going down quite steeply down the side of the paraboloid. If we were to turn and maybe aim in this direction, we might be going sort of this way, sort of up and around the paraboloid. If I was to aim like literally this way, I might be going around the edge of the paraboloid, like walking that actual circle. Depending on which direction you face, the slope on the mountain is going to be different. So we're now going to use a partial derivative and talk about it like it's an actual slope. But instead of saying rise over run. That said rum. I'm having a movie reference there. Rise over run, where you'd say change of y over change of x. That's not what we're doing at all. What we're saying is if we step in a particular direction, that's our run, will we be going up or down on the parabola? So it's actually a change of z over a change of, oh, well, what are we going to call that? So we're not going to use this notation, but it's going to represent a rise and run where we need to find a way to talk about, well, what direction is that? Well, these directions can all be talked about using vectors. So allow me to show you the definition of a directional derivative, and know that standing at one point on the graph, depending on which way you walk, the slope could be positive, the slope could be negative, the slope could even be zero if you're walking around the side of the mountain. And the type of answer you get depends completely on the direction you go on the three-dimensional graph. So here is our definition of the directional derivative. We have a function z equals f of xy, and u is going to be a, here's the big deal, unit vector. So the unit vector will be equivalent to us having the direction, but no magnitude that will interfere with our scale, so that when we do our rise over run, our run units are going to be 1 unit. That's not exactly the way it plays out, but that's a way to think of it. That might help you. So the directional derivative of the function in that direction of the vector is all this fancy notation. Direction of vector u, and even though I enlarged it, I could still make it bigger. I don't have a handy short notation for this, but look at this definition. This reminds me of some things from Calculus 1. I see derivative in there, but so if we have a unit vector that has two components, the concept is here then that we have the x and y are going to get changed in small increments, and this value of t approaches 0 is showing you, let's make those increments get smaller and smaller, and let's let the run get smaller and smaller. So the z is changing, f of xy, and the run is changing, both getting smaller. And when we evaluate this, we're going to get, well, if we substitute numerical values, we'll get a number, or we might get an algebra expression. It's not going to be handled the same way as when we learned the derivative of x squared, but there will be a type of shortcut involving derivatives, but it's going to take us a little bit to get there. So what we'll do next is an example utilizing the definition before we venture into, I wonder if there's a better way to do it. Okay? See you next time.